Yeah, thank you so much for a nice introduction. And I would like to thank the organizers for this opportunity. It's really a pleasure to be here. And yeah, so my talk is slightly different, but I won't go in too deep into the each of my subjects, but I would just give a just quick highlights on some of the works which I do and try to reflect upon in the end. So this is the title. So I work on three topics primarily. One is called the stellar archaeology and instrumentation in astronomy, and then exoplanets, which is the more fashionable topic in these days. So yeah, so these are my PhD students, and after yeah, I just looked at how many gender distribution here, and it clearly shows that fewer men. So it's just because I'm a woman, maybe I have more women students. I don't know. Is there a bias in that? I just, Preeti, when she mentioned about it, I started noticing this. So, so you can see the distribution. So I just jump into this first topic, stellar archaeology. Basically, this topic discusses about like this initial, after the Big Bang, if we have the primordial cloud of hydrogen, helium, and probably trace amount of lithium, which are made during the Big Bang. So if stars, low mass stars, which are formed from that cloud, would still be surviving now, just at the backyard around Milky Way. We should be able to see them. So the search for these very old metal poor stars, metal poor in a sense, they don't have any processed materials from stellar nucleosynthesis. They are mostly contains the Big Bang primordial nucleosynthesis elements. So far the searches show that there are no such primordial star which just has only hydrogen and helium. So the current record holder is -7 metallicity. What it means is it's like 10 million times they have lower iron content compared to the sun. So they have like 10 million times less. So that is the current best known metal poor star. So what we try to do is like basically chemically tag these old stars. So we use metallicity, that is the elements which are processed by stellar nucleosynthesis, those we call as metals. So the metal content in a star as a proxy for the time, so when it's formed. So we know like different masses of stars produces different elements during their nucleosynthesis, and when they explode or when they lose their masses, they will enrich the interstellar medium, and further star formations happen in the polluted material, and then the star will have an enriched composition. So the enrichment history you can trace back and kind of study the genealogy of a star. So that is what the stellar archaeology means. So here there are a couple of big questions in the field is, so we can actually trace back the nature of the first stars. Currently, JWST is the observations which can actually give the insights on very first stars, which are born in even JWST also, it cannot reach those epochs. So, but indirectly, we can probe the nature of the first stars, studying these first supernovae, which would have polluted the galaxy in the early time. So these nature of first stars, what we know is there are a lot of carbon. As you go to metal poor end, the stars have very enriched carbon abundances. We still don't know why compared to our solar neighborhood, we see a lot of stars which at metal poor end having high carbon abundance. We also see early enrichment of neutron capture elements. Neutron capture elements is basically beyond iron. If you want to, you can't fuse two iron nuclei and make heavier elements. So all the heavy elements, which are half of the heavy elements beyond iron in the periodic table, comes from the rapid neutron capture elements process. And half of the periodic table comes from the slow neutron capture elements process. So the meaning of slow and rapid, it depends on the neutron capture rates versus the beta decay timescale. So these are some of the questions. We want to understand what are the sites of astrophysical sites of these R process production, and also why there are enriched carbon abundances in the early galaxy. And also another insight is when and how the globular clusters, which are very old cluster of stars which are in the galaxy, what time they form, what epoch, what redshifts they correspond to, and during galaxy evolution, at what time of the galaxy evolution they are formed. So still the current proposal is either they formed during the star formation peak at redshift of 2 to 3 or during the reionization. We still don't know these possibility of these two. Uh, so I would just jump into the work which we have been doing. So this is a picture of the Hanley telescope, 2-meter telescope at the Hanley Observatory. And this is the Hanley Eshel spectrograph being assembled. And so we call it as a GOMPA, Hanley HESP GOMPA survey. So to survey the metal poor stars in our galaxy, because it's a 2-meter class telescope, we want to only observe the bright end of the stars. And this is how we use some of the low resolution surveys like SDSS, LAMOST, and try to fit model and try to identify the most metal poor one and observe them at higher resolution. So just some highlights from this GOMPA survey are this R process rich stars. You can see thorium detected in some of these stars, and also the lithium. So what one of the results is the carbon enhanced stars, do they have similar lithium as the non-carbon enhanced one? So that gives us a clue that whether it is primordial or it is formed from binary system. So we find that this carbon enhanced one has very similar lithium abundances as the non-carbon metal poor stars. And this is another thing which globular cluster escapees. So these are stars which are escaped from the globular clusters, because doing high resolution spectroscopy for globular cluster stars are non-trivial because of the high density as well as they are further in the galaxy. So escapees gives us an opportunity to probe them in very much details. So I won't go into a lot of details. I just want to just talk about these astrophysical sites of our process. So currently there are many proposals, theoretical proposals, that is core collapse supernovae, neutron star mergers and collapses, and magneto-rotational supernovae. So one of the direct evidence we all know is the gravitational wave merger, like which actually produced kilonovae after the gravitational wave event. So there is a presence of strontium line in the light curve, so which also indicates the processes, these gravitational wave event, that is a 2 neutron star merged and made gravitational waves. They also produce rich neutron capture elements. That is, neutron stars is full of neutrons. So as they come together, due to the decompression of the neutron star, you would make a lot of enriched neutron elements in the surface. It would start to make all the way from along the, what do you call is the neutron drip valley. You can make elements all the way to thorium, uranium, and further down. So, okay. So however, though we had a direct evidence, but theoretically what is predicted is stars which are below, so making 2 neutron stars and merge them takes some time, because you have to make 2 neutron stars, you have to have a massive star explode as a supernovae, and the core will remain as a neutron star. And 2 such neutron stars should have to merge together to make a neutron star merger event. So these time scales kind of dictate what metallicities these kind of stars could contribute to the ISM. That is, so that says that only at metallicities of minus 1.5 or less, greater than minus 2, or much later time in the galaxy, only these such events can make our process. But we see a lot of metal poor stars. These are the points. This is very old, like 2004 paper. You can see a lot of metal poor stars which have, at low metallicities, have enrichment in our process. So we also, our group also explored, like we wanted to look at if it is a supernovae produce alpha-rich elements. So the connection between the R process and alpha-rich elements, and we find that they are almost flat. So basically the core collapse supernovae do not produce these R process elements. And also we looked at thorium and europium ratios with respect to iron. Basically, when you have thorium, when it radioactively decays, it will become europium. So at any star which is recently formed would have more thorium compared to a very old star. So the ratios should have, but what we see is opposite trend. So which also indicates that there is a metallicity dependent making of these elements in the sites should have a metallicity dependence. So then further evidence, again, we want to see there are multiple sites is again this ratio. So strontium is a light R process element. Barium is used as a slightly high main R process elements. There are 3 different peaks in R process, which is strontium peak is called the light R process peak. Barium and europium peak is the main R process peak. Thorium and uranium are the heavy R process peak. So if you use that, like at metallicity of minus 2.5, there seems to be another site which is contributing to our process. So maybe the sites which are seeing at low metallicity is much different than what likely a neutron star merger. So here we try to address this problem using differential spectroscopy. Basically, because spectroscopy involves, you need to identify the star's temperature, other parameters of the star very accurately. So that would induce error in the derived abundances. So we took 2 stars which are very similar temperatures. You can see all their other lines matches except the neutron capture elements. So we did a differential abundances, and basically we wanted to see there are these 2 classes of stars, R1 and R2 stars. R2 stars are like 100 times enriched in R process compared to Sun, and R1 stars are about 10 times enriched in the R process elements compared to Sun. So whether, can you explain the R1 stars just by dilution of the ejecta of R2 progenitors? So what we find is you can't really, because if it is, so you would expect the light elements and the heavy elements should fall in this same line. So as you see that all the ion peak elements and light elements come from same progenitor, but R process elements are coming from different progenitors. Both lighter and heavier R process elements also come from a different progenitors. So this is also interesting to see, because the 2 satellite galaxies of Milky Way, what we know as Reticulum 2 and the Tucana 3, these 2 dwarf galaxies, they have R process enriched stars, but only one kind of R process enriched stars. So if it is a dilution process, you would see mixed. There are stars which don't have R process enrichment in these galaxies, but they don't have a mildly R process enhanced stars are not present in this one. So it's a kind of interesting thing to note why these 2 classes of object cannot be explained by one progenitor. That is something which we are, and this is a model and trend to, by fitting different neutron star mergers of different masses. So if it is the mass ratio of these 2 neutron stars are higher, that means a low mass and a high mass, then they seem to produce a lot of heavier neutron capture elements compared to a lighter one. So combination of these, the ejecta were compared, and we cannot still explain all the different classes of neutron star mergers. I'll move to the instrumentation part. Oh, sorry. Okay, I'll quickly move to instrumentation. So my journey into instrumentation happened like when I joined IIA, because I was, there was a project on, the Sunitra Giridhar is the PI of the project. So I was asked to take care of the purchasing and indenting all these instruments for the Handley-Eschel spectrograph. So that's how my journey into instrumentation started. But however, instead of not limiting to purchase processes, I also wanted to do work. So I had a PhD student who worked on developing a model-based calibration. So basically, when you design an instrument, you can predict what is expected at the end. So, but we never use that model to calibrate your actual data. So we use in this work, she has developed an analytical model end-to-end from the injection of the light, what is expected to the at the detector. So later, I think this same pipeline was used in Carmenes by the different groups, which for precision RV for exoplanet studies. So then this particular, probably this learning kind of helped me into getting into TMT instrumentation. So currently we are part of two instruments in TMT. That's the wide field optical spectrograph and the high resolution optical spectrometer. If you look at the wide field optical spectrometer, there are two, like in 2013, this is how the design looked. And now currently the design is different. And even the optical design is very different. So actually we contributed significantly for this change of this design. So IA has been, so this is part of so we had to prove to the team of the TMT that, so there was a mini study to assess the capability of different partners. So there was a mini study which putting all the partners together, and we had put up a expression of interest on modeling the end-to-end modeling of the spectrograph. And this is the team. So I led the team from India, and Sandy Faber led the team from the US, and Chuck Steidel and from Caltech. So what we showed is, so when you have an instrument like this, ultra-azimuth instrument, so you have to track the star, you have to altitude and azimuth, and also field rotation. So field also rotates. So that actually contributes to a lot of flexure. So if your optical design, so normally what is done in the Keck instrument is you closed loop manner, you move the detector to compensate for this field, any flexure. But when you move a simple movement, after this is the residual movement after so this is much, much higher. So the optical design, the original optical design had a high beta angle, that's out of plane angle of the grating, which was tried to keep the spectrograph compact, but it introduced a lot of distortion. So we noticed this, and so that was the review report. You can see that MCS study has provided a very detailed picture of the ability of current. MOBI was the original design concept to meet the scientific requirements of the baseline optical design. This goes into the heart of the instrument performance. The panel appreciated obviously the good collaboration and very honest report and evident effort contributed to this area. So I won't read it in detail. So this actually led us to get into the collaboration. And further, next step, I think Arun Surya here contributed a lot, actually developing a flexure compensation system. So that, again, you can say that FCS tool is a very powerful optomechanical design tool, and which was done by Arun. And so this is this is after the review, this team. So you can see few women, of course, like that is again obvious from here. So further, we also checked our flexure compensation with applying it to the Keck DMOS spectrograph, and we were able to match it. And then there was a call for a second generation instruments, and India, we proposed for a high resolution optical spectrometer, and that was actually very favorably considered, and we were able to India could lead an instrument from for high resolution. And these are some of the designs. I wouldn't go into that, but in terms of performance, it's a very unique design, which is compared to other 8 to 10 meter class telescope and GMT and ELT. The design choices are it was appreciated. We were able to go both slit mode and fiber mode, and also for have a blue sensitivity. So then this good collaboration also led to further collaboration to IAA. I think Ravi Banyal and Arun are the main people. I am not part of this. I am just only provided the initial connection to those groups. So this is a direct imaging of exoplanet instrument. It's going to be commissioned in early next year. And so you can see this clearly shows planet signal versus a speckle. You can see the speckle varies with the wavelength, but however, this. So I'll just quickly move to exoplanet science. So again, we looked at host stars, and one of our results is actually the giant planets hosts are carbon poor, which is that is one of our interest results. So basically, it says that basically dust plays a most role than ice-rich um, uh, ice-rich dust. All right, yeah. So this is again first time we observed exoplanet transits with our 2-meter class telescope, and these are the fitting. And I'll just go into the final part, what I want to reflect upon. I kind of moved into 3 different areas, but still what I feel is what stellar spectroscopy is my favorite, or that is where I feel I am recognized in the field. Though I got into instrumentation, maybe most people in India and probably within TMT collaborations would know me. However, I have also heard sometimes when people say that I'm leading high resolution optical spectrograph for TMT, then they thought I am being a bit naive. I don't know the challenges of the projects. So that is something I want to. And so overall, I found that the entire journey was enriching. I was very happy that I learned many things. And again, exoplanet field, it's very rapidly evolving. And I don't, at this pace, if I don't put in a dedicated time, I don't think I could really make an impact in this field. So this is my conclusion. So basically, it is good to balance when you're venturing into new areas. And also you also want to people recognition in a given field takes some time. So early career scientist, when you venture into instrumentation or any other field, like um, it is good, but take a balance between what you want to. And also in a group, again, I was fortunate to always lead a group rather than being part of it. So I was able to be recognized because of I was the lead. But if you are part of the team and women get a credit for their contribution, is again a questionable thing. Yeah, again, in the Indian context, I feel that instrumentation provides a valuable addition because you would know the administrative and purchase processes and rules. So if that would actually help in as you grow in the Indian setting. I would feel that instrumentation in an Indian setting, it was good, very beneficial for me. But I really, how many people in internationally would know me for instrumentation is still, I still feel an outsider in an instrumentation conference. Yeah, thank you very much.
Thanks, Sivarani, for the nice talk. Questions for her?
Thank you for the fascinating talk. So the exoplanet, can we also detect some biosignature in the exoplanets with the studies?
Yeah, so with like biosignatures are probably a JWST thing, like not for a 2-meter class telescope. Again, for transit spectrophotometry is still a challenge for in ground base because we are looking at slit losses and the high frequency variations. So even a big telescope like Gemini gives same, I don't have the slide, like a 2-meter class telescope and Gemini would have very similar error bars on the ground. But a smaller telescope on space would do much better in terms of, but in the high resolution transmission spectroscopy, for example, O2 biomarker biosignatures can be done with TMT or the big telescope or ELTs and TMT, because in high resolution, what you are looking at is the cross correlation signal, because when the planet crosses the stellar disk, with respect to the star, the planet is moving in velocities. It's not very precision. You don't have to have this centimeters per second, but planet is moving at several meters per second or even kilometers per second. So which you can actually detect their cross correlation signature and directly derive the signatures. So that is for ground-based astronomy, this high-resolution spectroscopy of O2 lines, 7,700 regions. So those are very good. Yeah.
So
ELT
there
could
has
do
been
it.
some advancement in this field. So we could actually hope for like having some like discovery or like, you know, what I mean, the biosignature in the upcoming decade or so. Do you think so?
Yeah. I still don't feel myself an expert. I'm not always catching up in this field. Technically, I'm fine, but still in terms of what is latest and modeling aspects, I still lack expertise in that area. But yeah, it is a lot of things are coming up in terms of it is evolving as the entire branch of like astronomy. Exoplanet science is branching out into a entirely different a subject, including chemistry, biology, and like all these dynamics, like all these, yeah. Yes.
Thank you very much.
Question quick. We have to move to the next speaker.
Just a comment. Sivarani is too modest to make claims about herself. About this HROS, I know this very closely because I was part of TMT SAC then. There were several white papers submitted from various other TMT partners, and the TMT project, after very rigorous review, chose India to lead with Sivarani as its head. So that means something. And I also. I had also attended several TMT science forums with her. So from India, they only know Sivarani. Everybody knows Sivarani, and then everybody seeks Sivarani. And so it's not she doesn't sort of. So I just wanted to congratulate her for that. I mean, what she has achieved in instrumentation, although she feels she still is an outsider, but I think it's tremendous. What you have achieved, Sivarani, and I don't think anyone in India in instrumentation can boast of that.
Thank you, Madhava, for that.
That. Thank you, Sivarani.